Alright, in this lecture video, we're going to continue looking at the randomized complete block design, and in particular look at the specifics of how to perform the analyses and so forth. So let's first talk about an introduction. Let's look at a model for the randomized complete block design. So the statistical model for the randomized complete block design can be written as a means model in the following way. So we've got y sub ij being equal to beta sub I plus mu sub j plus epsilon sub ij, I going from 1 to r, j going from 1 to t. Now we need to be careful and make sure we understand what these subscripts represent. Different textbooks, different resources will maybe switch the order of the indices, so we need to make sure that we understand how we're using them in this particular set of notes. So y sub ij is the response measured on the experimental unit receiving treatment j within block I. So the first subscript, the I, corresponds to the block number, and the second subscript, j, corresponds to the treatment that has been assigned to an experimental unit. Now, beta sub I is the effect of the ith block on the response variable y. Mu sub j is the mean treatment response under treatment j. And then epsilon sub ij is the random error associated with the experimental unit receiving treatment j within block I. So again, this is the means model representation of the statistical model for the randomized complete block design. The effects model for the randomized complete block design looks similar, the only difference being that now instead of having mu sub j in the model, we have a mu plus alpha sub j. So again, the response, y sub ij, in this case is equal to mu plus beta sub I plus alpha sub j plus epsilon sub ij. Y sub ij has the same interpretation as it did in the means model. But now on the right-hand side we have this mu, and the mu represents the overall population mean across all of the T treatments that are being used in the experiment. Again, beta sub I is the effect of the ith block on the response. And then we have, I've got mu sub j that needs to be alpha sub j. I need to fix that. So alpha sub j is the effect of treatment j, the impact of the treatment j on the response. And then finally, as before, epsilon sub ij is the random error associated with the experimental unit that has received treatment j within block I. Now let's look at the model assumptions. The first assumption is that the block effects, the betas, beta sub I, these are independent random variables. They're not constants, all right? These are assumed to be random variables because we're not wanting to just make inferences across the blocks in this particular experiment. We want to be able to make broader inferences, broader conclusions. And so we consider and treat the block effects as random effects. All right, they're random variables with mean 0 and a variance which is denoted by sigma squared sub beta. And then if we need to make inferences involving the blocks or those random effects, then we would further assume that the block effects are normally distributed. The model error terms, the epsilon sub ij's, are again random variables with 0 mean. The variance of the error terms is, again, as it was in the completely randomized design, denoted by sigma squared, and the error terms are assumed to be stochastically independent of each other. In addition, regarding the block effects, the random block effects, and the random error terms, they are assumed to be mutually independent as well. So the block effects and the error terms are assumed to be independent of each other as well. Now, the population or treatment means, mu sub j, or if we're working with an effects model, the treatment effects, the alpha sub j's in the effects model, can be either fixed effects or random effects, as was the case for the completely randomized design. So first, if they are considered to be fixed effects, which I think in most situations they would be, then the mu sub j's are unknown constants with arithmetic mean equal to this overall treatment mean mu, right, which we had in the effects model. All right, if we are thinking in terms of an effects model, then we can say that if the treatment effects are fixed effects, then the alpha sub j's are again unknown constants, and in this, if again thinking in terms of the effects model, the alpha sub j's, the effects add to 0. All right, and so what the alpha sub j's represent are the differences between the treatment means and the overall treatment mean mu. So alpha sub j is equal to mu sub j minus mu. And again, because mu is the arithmetic average of the treatment means, the mu sub j's, then necessarily the alpha sub j's would add to 0. So that's a constraint that exists among the treatment effects, the alpha sub j's. Now, if the treatment effects are random effects, then the mu sub j's are random variables assumed to be normally distributed with a mean of mu and a variance of sigma squared sub tau, tau for treatment. Or again, if we think in terms of the effects model, then the alpha sub j's would be random effects, random variables. They would be assumed to be normally distributed typically with a mean of 0. All right. Now, well, they will always have a mean of 0 and a variance which is denoted by tau. Sigma squared sub tau. But if we, in order for inferences to be made, we often need to make assumptions about the particular distributional form of the alpha sub j's, and so we would use normality in many cases. All right, so now let's talk about the advantages, the disadvantages, and the uses of the randomized complete block design. So here are some of the advantages of the randomized complete block design. The first is that, and this is really the important one, is that effective blocking, and let's emphasize effective, all right, because sometimes blocking can be ineffective if we don't understand the heterogeneity in the experimental material. Then efforts at blocking may very well be ineffective. But if an experimenter does have an understanding of the nature and direction of the heterogeneity in the experimental material, then quite often, very often, blocking will be effective. And when blocking is effective, then it decreases the unaccounted for variation in the response. And the result of that is that it increases the power of statistical tests, and it increases the precision of the estimators. And that's always a good thing. That's really the whole point of experimental design, is to be able to perform analyses that are valid, that are consistent with the design of the experiment, and to come up with designs that give us more power in our statistical tests and more precision in our estimators. Right? So that's really the bottom line of all design right there. All right, is to help ensure that we get the most bang for the buck, that a researcher gets the most information from a given amount of experimental material, time, money, and other resources. Now, one of the other advantages of a randomized complete block design, one of the nice features or characteristics of a randomized complete block design, is that any number of blocks can be used. There's really no theoretical restriction. There's no mathematical or statistical restriction on this. All right. The only limitation is how many blocks of experimental material are available to the researcher. In addition, any number of treatments can be used as long as each block can accommodate that number of treatments. And so now let me just explain this a little bit. When we say that any number of treatments can be used, that is true. There's no mathematical limitation. There's no statistical limitation on the number of treatments that can be used in a randomized complete block design, as long as each block is large enough to accommodate the full set of treatments that are being considered. Now, there are some logistical constraints, some limitations that are imposed by the material itself. And so, for example, if the blocks are not large enough to accommodate all treatments being used in the experiment, then that right there is going to be the limitation. So the limitation is more on the size of the blocks than any kind of theoretical or mathematical or statistical limitation. And remember, when we talk about the size of the block and the nature of the blocks, the shape of the blocks, and so forth, the whole point of blocking is to group experimental material in such a way that the experimental material within a block is as homogeneous as possible. And so what happens, that's the guiding principle, but what happens as we increase the block size, then we decrease the homogeneity of the experimental material within the block. By increasing the size of the block, we increase the heterogeneity of the material contained within that block. And so that is the other caveat here that we need to be thinking about and need to understand when we say that any number of treatments can be used as long as each block can accommodate that number of treatments. We need to understand that as we increase the block size, then the experimental material within blocks will become less homogeneous, more heterogeneous, and that would defeat the whole purpose of blocking. So there are physical limitations, all right, but in terms of the statistical and mathematical property or principles, as long as a block contains homogeneous material and there's enough material to have the full suite of experimental units within each block, then there's no limit. Okay, the next advantage or feature, characteristic of a randomized complete block design is that the statistical analysis is still relatively, well, this says starlight forward, maybe that too, but relatively straightforward, at least when we have full data, all right? And I see I've got two typos. Let me fix those real quick. Okay, so again, the statistical analysis is still relatively straightforward, perhaps a little bit more complicated than the analysis for a completely randomized design, but not much more complicated, all right? Now, I will say that this is assuming that we don't have any missing data. If we do have missing data, then that complicates the analysis, at least when we're doing it by hand. All right, and then another really nice feature, nice characteristic, which is an advantage of the randomized complete block design, is that additional blocks can be added to an experiment when needed to increase the number of replications without increasing the complexity of the experiment or its analysis. And this is especially true in those situations where, for example, blocks, there are many situations where time is a blocking factor. So perhaps you're involved, maybe you're in a lab, maybe you're doing chemistry work or biology work or whatever. Even this can be the situation, even if you're out in the field, or maybe you're doing work in a greenhouse, all right? And you are, so in a greenhouse, for example, right, you're being, the plants that are being grown in the greenhouse are being exposed to solar energy. There is humidity, perhaps the differences in humidity as time goes on in different seasons or different months in the year, although that's they try to control that, obviously. But there can be differences due to things like that. So differences in temperature, solar radiation, humidity, and so forth. And so quite often, the point in time at which an experiment is done with a full set of treatments constitutes a block for that experiment. And so with a completely randomized design, it's very easy to add additional blocks to repeat the full experiment or at least, a block of a replication of the experiment several, over time. And so you're increasing the size of the experiment by doing additional replications, and oftentimes those replications are treated as blocks, okay, because of the potential differences in, again, things like humidity, temperature, solar radiation, whatever. And so if a researcher chooses to do that, it does not complicate the analysis of the data from the experiment. So that's a really nice feature. Now let's look at some of the disadvantages of the randomized complete block design. So the first is that blocking decreases the number of degrees of freedom associated with the error term. So ineffective blocking, okay, now we're talking about that situation where perhaps a researcher didn't have a lot of information about heterogeneity in the material, and because of that, maybe they didn't block appropriately, or at least block effectively, okay? So ineffective blocking can actually decrease the power of tests and the precision of estimators, because blocking, when we do the analysis, what that's doing is it's decreasing the number of degrees of freedom for error, all right? And so when you decrease the number of degrees of freedom for error, if you look in the F table, what happens is that the critical point for an ANOVA, it increases, right? As the denominator degrees of freedom decreases, the critical point increases, and so it makes it harder to reject that null hypothesis. And so if the decrease in the unaccounted for variation is not enough to compensate for the increase in the critical point that results from the decrease in the number of error degrees of freedom, then that would result in a decrease in power and a decrease in precision. The other disadvantage is that missing data complicates the analysis. And if you have too many missing values, then, for example, let's suppose that you have a block. Maybe you have all of your blocks except one that has complete data. If you've got just one missing observation in that block that has a missing one or more missing values, if you've got just one missing value, that can be dealt with in a fairly straightforward way. But if you have more than one missing value, then it really becomes problematic to do the analysis. And oftentimes you'll just want to throw out that block completely just to preserve the ability to do the analysis in an easy way. Now it's listed here as a disadvantage. It's a characteristic, all right? It's just the nature of the beast here, that the efficiency of the randomized complete block design decreases as the number of treatments increases, and therefore the block size increases. And this is because of what I was saying before. As the size of the block increases, the homogeneity of the experimental units within the block decreases, right? Larger blocks are not going to be as homogeneous as smaller blocks. Everything else equal, right? And so that diminishes the efficiency of the randomized complete block design as the number of treatments increases. Now, this next one is also listed as a disadvantage, but it's really just a characteristic that we need to be aware of. If there is more than one source of extraneous variation, and I really should include extraneous variation here, so I think I'll do that real quick. All right, so if there's more than one source of extraneous variation, then it would be better to use a different design, one that accounts for not just one source of extraneous variation, but two. All right. For example, if there were two known sources of extraneous variation, then we would want to use a different design. We'll get into that design after we talk about the randomized complete block design. And then finally, if the experimental units are in fact all homogeneous, right, so the blocking is really not necessary, then the completely randomized design would be more efficient because it has more degrees of freedom for error. All right. But if that was the situation, if the material was homogeneous, then the experimenter would probably have a pretty good idea of that and choose to use a completely randomized design. Anyway, but just keep in mind that if we don't have a good reason for blocking, and if there is good reason to assume that, or to believe that the experimental material is in fact homogeneous, then a completely randomized design is probably going to be a better type of design for a given situation, because it's got more degrees of freedom for error, and so therefore it would, because of that, as long as there's not any unexplained variation, or at least not much unexplained variation, the completely randomized design would be more powerful. But having said that, the randomized complete block design is probably the most widely used, the most prevalent design out there, because there are so many situations where there is a lack of homogeneity among all of when you consider all of the experimental material to be used in an experiment. It's not all homogeneous. There is heterogeneity, and researchers deal with that by blocking. Okay, finally, the uses of the randomized complete block design. The primary use, the primary purpose of using a randomized complete block design, again, is to remove one extraneous source of variation from experimental error. Now, I want to make sure that I'm pointing this out. We're talking about extraneous sources of variation. If a source of any treatment that a researcher might choose to use in an experiment is a potential source of variation, if an experimenter is specifically and explicitly incorporating a particular factor into an experiment to be part of the treatment structure, then that is not an extraneous source of variation. That's a source of variation that is of interest, and so you would treat that as a treatment rather than as a random source of variation. So we're talking about sources of variation that we're really not interested in modeling or making inferences about as part of our treatment structure. So again, variation due to an experiment being performed across different months or different seasons, or experiments being conducted by different lab personnel, or experiments being conducted on different batches of manufactured material to which one or more treatments are being applied. All right? In those situations, we're really not interested in modeling and understanding and making inferences about variation due to different lab techs, or variation due to different batches of manufactured material. Okay, we're interested in the impact on the material of the treatments that are being specifically utilized in the experiment. And then finally, the randomized complete block design provides unbiased estimates of the means for the blocking factors, which does provide the researcher with more information about the experiment and the experimental material. Now, how might this be useful to a researcher? Well, again, in order to utilize blocking effectively, a researcher has to know something about the experimental material to which he or she is applying the treatments. And so let's take as an example an agricultural research field. All right, and so a researcher, in order to perform effective experiments on a particular field, needs to understand, is that field homogeneous with respect to features and characteristics that could impact the response of interest, or is there heterogeneity, all right, that would cause variability in that response? Now, that can be determined by repeated experimentation by considering for example, looking at the means of the blocking factors. So if a researcher sees variation from one block to another in terms of the means of the responses, then that is an indication to the researcher that there is underlying heterogeneity that can impact the response, and that so for future experiments, the researcher will have more information that can guide their decision as to how they want to conduct an experiment. what is the, is there heterogeneity? Is there some kind of a gradient? If so, in what direction is the gradient? In fact, this could lead to a researcher sampling different parts of the field to get more information about the nature of these kinds of things. All right, and so that's another use of the randomized complete block design. Understanding the potential differences from one block to another by looking at the means of the responses from the various blocks. Okay, finally, let's look at the randomization process for the randomized complete block design. And we've looked at that in a previous lecture video, but we'll just list it here. And so the conceptual idea, all right, is that first the researcher has got to form the blocks. So from the experimental units, of which there are T times R, T being the number of treatments, R being the number of blocks, form the T times R experimental units into R blocks, each of size T. Okay. And then separately, within each block, randomly assign treatments to the T experimental units within the block. So for the first block, randomly assign each of the T treatments to exactly one of the experimental units within that first block. And then separately, a completely different randomization schedule. For the second block, randomly assign each of the T treatments to exactly one of the experimental units within that block. And so forth up to the last block, the Rth block. Randomly assign each of the T treatments to exactly one of the experimental units within that block. Now again, separate randomizations have got to be used for each block, and that's very easy to do, regardless of whether you're using computer software to do it, like I showed you in a previous lecture video, or if you're doing something as simple as pulling slips of paper out of a hat. All right, and so I'll let you think about the details of how you could implement the randomization process for a completely randomized design, and see what you come up with. But these are the criteria that have to be satisfied in order for that process to be appropriate for an RCB design.